this past week amongst us. I guess that's an improvement. But I'll have an announcement tomorrow about precautions to take next week before you depart, so that you don't end up in isolation before you have to leave the dorms. At 3:30 today, Freddie Boucher is going to give an informal talk at the request of several of you on mitigating climate change, recent trends in the energy and ecology transitions. This seems pretty appropriate this week with the heat wave in Europe. So that's not going to be recorded. It'll just be right here, very informal. And so you can see the poster boards are up. And so Freddie anticipates speaking for about 45 minutes, taking questions, I'm sure. And so then you can set up your posters for the final poster session. We'll have our poster blurbs here as usual at 6:30. Okay, Steve.
Thanks, Brad. Thanks everybody for showing up again. It's nice after the first day, first lecture. So let me just remind you of what I talked about last time. So I gave some motivation, most of which came from astrophysics, though some from plasma physics, about why we're interested in the interaction between mean flows or mean magnetic fields and turbulence. I talked about Jupiter's jets, the solar cycle, and I talked about this, the importance of the fact that for all these objects, there's some constraint. It might have come from rotation, it may have come from magnetic fields in the plasma physics case. I said there were two paradigms. Actually, I think there are three, but I only talked about two. So I said the two paradigms for these interactions are that you could have mean flows and then they go unstable and give you turbulence, and then somehow the turbulence comes back, acts back, and somehow modifies the mean flows. Or, and this I think is the kind of more tricky one to get right, you have the turbulence plus something which is going to engender correlations in the turbulence. That could be rotation or stratification or something. And that, some breaking of some symmetry leads to the generation of mean flows or mean fields, mean magnetic fields. And then they can, of course, come back and act back on the turbulence that's generating it, and then we get into some self-sustaining process. Another one which might interest Nigel particularly is there are situations where you get analogs of transition. So this one goes something like this. You have a mean field of perhaps finite amplitude. Okay, it goes unstable in a way very similar to maybe pipe flow or something, which goes unstable and it gives you turbulence. And then the correlations in the turbulence are just the right type of correlation to give you back the mean that you wanted to go unstable in the first place. This is sometimes called a bootstrapping type of situation, because you need these correlations to be just right to generate the mean field that goes unstable in the first place. And there are examples of this, certainly dynamos that work this way. They're sometimes called essentially nonlinear dynamos because you need a field of finite amplitude to get them started. And for those of you in the know, the magnetorotational instability, which is important in some disks, the dynamo associated with that is one of these. Okay, so that was the motivation. I then said we're going to consider an evolution equation that looks like this. Q is a vector of state variables. And I spent an awful lot of time, possibly too much, saying, well, we can have a Reynolds decomposition. Q could be decomposed into a mean. And I talked about lots of different ways you could get your mean, plus some fluctuations, okay? So let's just see, why do we do this? And what does it mean? Okay, so let's carry on. So this was equation 1 that I had up there. So what am I going to do? Okay, so this is the quasi-linear approximation. I'm going to take equation 1, which is that one up there, and I'm just going to average it. I'm not going to keep writing out the forcing. So I'm just going to average equation 1. So this is quite easy. I take the derivative and average it. This is a linear term, so this just looks like the linear operator acting on Q bar. Now then, my nonlinear term, if I expand Q into Q bar plus Q prime, you can see when I do a not quadratic nonlinearity, I'm really going to get 4 terms. But not all of these appear in the equation for the mean. So I'm going to get a term which looks like the interaction of the mean with itself. That's an important nonlinear term. The terms which look like the interaction of a mean with a fluctuation, Q bar, Q prime, when I multiply the two together, they look like a prime. So they're going to come and appear later on in the fluctuation equation. But then I'm going to get a term, I said really is, Q. This I think is the key term for the whole of the rest of the, for the whole of the 3 lectures. This is the term where the fluctuations interact with themselves non-linearly and they act back on the mean. So in the language of triad interactions or something like this, I'm going to call this a mean going to mean type term. You can see this is a mean interacting with a mean and it's coming back in the mean equation. And I'm going to call this a fluctuation going to a mean. So my notation is these are the things that are going into the operator and this is the thing that's coming out, okay? So this is somehow has managed to become equation 11. Okay. Okay, so this is fine, but what we don't know this. If we just wanted to solve for the means, really we want to get a handle on how the means are behaving, you know, we need to know what it is. So what do? Well, we write down an equation for the fluctuation. So the way to do that is take equation 11 away from equation 1. So I'll just write this out and then I'll explain where everything has come from. Oops. Okay. Okay, all I've done is taken one equation. Oh, yes, thank you. I do. Yeah, sorry, I've got that wrong. Thank you, Ellen. My bar is too long. Never thought I'd say that. Okay. Thank you. So all I've done is that, you know, this term here has been taken away from the full term. Okay, so that's why I've got this funny minus. And it kind of becomes obvious when you think about it, writing it in terms of the interactions. So this is these are the, let me get this way. These are the terms where the mean is interacting with a fluctuation to give me a fluctuation. Yeah. And these are the ones where the fluctuations are interacting with the fluctuations, not to give me a mean, but to give me a fluctuation. Those ones there. And so what I do is I work out the full fluctuation interaction and just take away that bit which was gone back in the mean equation. Okay. So this is equation 12. And this term here, this one here, I'm going to call G. And it's a fluctuation term. So I'll just call it G of Q prime, Q prime, okay? I'm just going to use that as shorthand. And this, okay, let's have a look at this. In terms of Q primes, this is an equation for Q prime. This term only has a Q bar and a Q prime in it. It only has one Q prime in it, as does this one. So this term is actually linear in Q prime. It's not linear full stop, but it's linear in Q prime. So I'm going to write this as some other operator, L of Q bar, acting on Q prime. Okay, that's this term here. Is everybody happy with what I've done? I've just taken one equation from another and then called the terms something. Okay. So at this point, I haven't done anything. I mean, in a sense, I've split the equation up. I could go away and solve this equation and this equation together, and all I'm doing is solving the full equations. So there's no point in doing that unless I do damage to my system. Okay, so now I'm going to do damage to my system. And I'm going to do the most amount of damage I can do. The most amount of damage I can do, this term is going to prove to be painful. Okay, so I'm going to set it to 0. Okay, so this is the QL approximation. So for the quasi-linear approximation, I'm going to set G of Q prime to be equal to 0. And this term is such a pain, such a painful term. It has a name. Okay, it has two names, in fact. So sometimes polite people call it the eddy going to eddy nonlinearity, or the enal term. Okay, and that tends to be in the turbulence literature. So you were setting the eddy going to eddy, or as I've called it here, the fluctuation go to fluctuation, nonlinearity to 0. Or in dynamo theory, in mean field electrodynamics, it's called the pain in the neck term. And this was, well, okay, there's some debate about who said this first. Most people attribute that to Keith Moffat. But actually, Paul Roberts told me he said it first. And I can kind of believe that, Paul Roberts. So. Okay, so this is the pain in the neck term. Okay.
Are you sure they use that?
No, yeah, so some people call it the PIA term, and I'll let you work out what A stands for yourself. Okay. So far, I've written everything in terms of just terms, equations. We can think of this if we're thinking of doing a spectral decomposition, and our averaging procedure is to take the mean. So we'll think about averaging over one coordinate. We can think of this in a different way. So let's go over here and think about the type of interactions we have in the fully nonlinear solution. So imagine I have, Q is a function of wave number in one direction, and I'm going to take the interactions, okay? So this is an interaction diagram. So there are 3 different sorts of interactions. There's a mean, which can interact with a fluctuation, and I'm going to say that fluctuation has wave number k, okay? And that could give me a fluctuation. So that is that term there, that LQ, Q prime, okay? I could have, a fluctuation interacting with a fluctuation to give me a mean. In the notes, I've drawn a minus k with just an arrow going the other way, but I mean the same thing. So this is the important term, this one over here. And I could also have, of course, I could have fluctuations interacting with fluctuations. So I could have a wave number k1 interacting with a wave number of k2. Give me a wave number k1 plus k2. And this is a fluctuation, fluctuation goes to fluctuation interaction. So the quasi-linear approximation just involves getting rid of this and just keeping these. So we're really keeping the fundamental thing, which is the turbulence interacting with itself to give you a mean, the mean interacting with the turbulence to give you the turbulence. But we're kind of throwing away quite a lot. We're throwing away any kind of turbulent cascade or inverse cascade. This is like wave numbers interacting with each other, which are not means to give the other turbulent modes. So when people study homogeneous isotropic turbulence, essentially this is what they study, the bit we've thrown away. So the methods, I want to stress, the methods I'm going to be talking about today and tomorrow are absolutely useless for studying homogeneous isotropic turbulence. Do not do it. And if you don't believe me, read Frisch's book where he explains how useless they are. He doesn't say they're useful for anything, he just says they're useless. But really they're useless for homogeneous isotropic turbulence. Okay, so please bear that in mind. If you don't have, and we'll come back to this, if you don't have a systematic mean flow or mean field, then throwing away this term in relation to the other terms, you can see it's a bad thing to do because the other terms are zero. If you do not have Q bar, throwing away that in all the other terms in the Q prime equation is definitely a bad thing to do. So this here, we've thrown away this interaction. This is an example, and there'll be more examples coming your way, of what Creighton called constrained triad decimation. Okay, is everybody happy with that? Good, so I've made a kind of approximation there. So the first thing you're going to want to know is when is it, well, what does it mean and when is it appropriate to make that approximation? So just a couple of things to note. So QL is a conservative approximation, and it is a conservative approximation because essentially it's an example of constrained triad decimation in pairs. So we take out interactions and we take them out self-consistently such that global, linear, and quadratic conserved quantities remain conserved. So this is a nice property. Obviously, in absence of driving dissipation, so energy, entropy, things like that would be conserved by it. So let me just write that down. So in absence of driving, dissipation, etc., total energy, for example, and linear and quadratic invariance are automatically conserved. For those people who are interested in dynamos or mean field electrodynamics, which I'll say something about, but for those experts, you can think of QL as being a self-consistent mean field theory. Mean field electrodynamics. And I'll come back to that a bit later on. Okay. Everybody happy? Good. Okay, I'll leave that up so you can see kind of where we're going and what we're doing. So the first thing to say is, when is this thing, I've made this approximation, but when am I allowed to do it? And the answer to that question is, I don't know. But there are some situations where I can say this, I can definitely do it a priori, okay? Let's do those first. and I'm not going to go into too much detail because possibly Keith touched on this a little bit, but let's just formally, QL is valid. Well, it's valid when this term here is asymptotically smaller than the other terms. You can just throw it away, right? So when G is asymptotically small, oh, you know what I mean. You shouldn't stand too close to the board. Small compared, well, with the other terms, right? So I had a term which looked like this. And this is a property of the nonlinear terms in the equation, right? It's a property of the nonlinear terms. So sometimes it's quite hard to get a handle on this a priori. So I'm just going to do this by example. So of course, the famous nonlinearity u dot grad u in the Navier-Stokes equations. Okay, so u dot grad u. So I might compare. So what would this look like? So I might compare u bar dot grad u prime with something that looks like u prime dot grad u prime. Some of this term goes into the mean, it's true, but quite a lot of it goes into the fluctuation. So as a first order attempt, I might try and see what the size of this is in relation to this one, or I might try and compare it with, say, dt of u prime. That's another term in the equation. And if this term is smaller than these, then we're kind of okay. Let's try a different color. So clearly here, I can see one way this thing is going to work. If the mean is very much bigger than the fluctuations, so the fluctuations are weak, we're in the regime of weak fluctuations, then I'm going to be able to throw away terms which are quadratic in the fluctuations. Comparing this one with this one is a bit more tricky. You have to put in correlation lengths and correlation times and things like this. But I won't go into where we've got this from. You just kind of put u prime over a typical time on which u correlates. Okay, so this is the correlation time of the turbulence. And then I'm comparing it with this. So I've got a u prime there. I've got a gradient of it, so I put a correlation length in, and then the u primes cancel. So I'm just left with 1 over tau c, very much bigger than u prime over LC. And so obviously, conditions would be if u prime over u bar is very much less than 1, that would allow me to do it. So if u prime over uc is very much less than 1, or u prime tau c over LC is very much less than 1, then I can definitely apply this. And this is called the Kubo number of the turbulence, in the case of the nonlinearity being. So if this is very small, I can get rid of those nonlinear terms. Yeah.
In the nonlinearity, you put it one way around.
Yeah.
Scales.
Yeah, that's true. You need to be a bit more careful than a bit here because U bar, well, we're going to assume U bar is on a longer length scale than, so when you do it a bit more carefully, you get the same answer. Yeah.
What did Kubo do? I don't think I know about his name.
Okay, so Kubo didn't really do very much in this actual field. It's just an analog of what Kubo did in other fields applied to this nonlinearity or applied to, yeah. But for some reason that name is stuck. I don't know why.
The same as the Kubo with
Yeah.
formulas and all.
Yeah. Yeah, Nick.
I was just curious, if, like, since you drew pictures that look like Feynman diagrams or using terms like mean field theory, what's the relationship with normalization group, or is there one?
See, there's a guy over there at the back. Go and talk to him. Okay. Yeah, he's the best person to talk to about that. You just ask.
Attempt to do the normalization calculations using these kinds of
These are all things we're interested in doing and looking at. Yeah, absolutely. So
wild diagrams.
if you know how to do all this stuff, then come and talk to me and Brad. I think it's fair to say, isn't it? Yeah. So, okay. Yeah, just to say, just to remind you where we are, if these are true, then QL is valid. The problem, of course, with this is, you know, before I start a calculation, I don't know what the correlation time of my turbulence or the correlation length of my turbulence is. So this is something I only know after I've done the calculation. So, yeah. So we have to go away and just try things out and see whether the quasi-linear approximation is a good one. I mean, you can say I'm only going to consider turbulence with correlation times of, you know, that satisfy this and correlation lengths of this. And in mean field theory, people try and do that. Mean field electrodynamics, people try and do that. They postulate a priori that you're in that regime, but I don't quite see a way of guaranteeing that a priori in any given situation.
It depends on how you define outer
Yeah.
scale, and that's an outer scale velocity.
Yeah. No, absolutely.
It would be small. That may not know the boundary.
So as I said, there are cases where you do know before the event. So I'm just going to give some examples where you know a priori. So obviously, if you've got low amplitude turbulence, so I don't know, you're in weak wave turbulence or something, and that's interacting with the mean flow. So you could have, let me push that up a bit. Sorry for those copying down. You could have a separation of timescales. Between the mean and the fluctuations. And that may be guaranteed by the presence of fluctuation, by the presence of a small, asymptotically small parameter, so, or a large parameter. So just give some examples. So planetary atmospheres of what's called Izonostrophy parameter. So that's a large, that's a parameter which essentially measures this separation of timescales. And so there's a nice paper by Freddie Boucher talking about that. for those people who do, I want to leave that up there, so I'll go over here. Who do dynamo theory. People can see that. So in dynamo theory, this approximation has a name, in fact, it's called first order smoothing. So there's some examples in the context of the Earth where the induction equation at least becomes quasi-linear. So I just picked a random paper here, which says Keith and I as authors, so it's not all that random. Then in the present, in accretion disks, there's a very nice Squire and Bhattacharjee, where they consider quasi-linear evolution, essentially.
Steve, I would just point out that the parameterization stuff I was talking about yesterday, essentially not assuming that G is 0, but that only a few elements of G are worth bothering with.
Okay.
And those might be easier to predict than the generic form for all the nonlinear terms.
Yeah, hopefully.
So select a few and then put them into the rest of the system the same way.
Yeah, hopefully in the next lecture, I'll get on to saying a little bit more about things that tie in with what Baylor said as well. Okay, how are we doing for time? Okay. Is everybody happy with that? So what are the properties of this equation? Well, as I said, it's called the quasi-linear approximation for a reason. The reason is that the equation for the fluctuations is formally linear in the fluctuation. That is kind of nice. It allows you to make progress. And so this is something, I'm not going to dwell on this point because Brad put something in the Slack channel. So, but this is where we're going to ask for help from you guys. So these equations exhibit infinite U1 symmetry. So if we have a look at the equations for the fluctuations, because we're linear in the fluctuations, if we're talking about coordinate averaging, the QL equations exhibit U1 symmetry. What do I mean by that? Well, you guys know all this better than I do, certainly. So what does this mean? It means that in QL, the phase of each fluctuation, can be changed by an arbitrary amount, and you still get the same equation, right? So if I have Q with a wave number M, I don't know why I started calling it M as opposed to K, it doesn't really matter. This is a symmetry. So the question Brad would like to know, and you're going to tell him, so this is your homework. What does this invariance give us? So does the invariance of the QL equations under phase rotation, we're doing there is rotating the phase, correspond to an infinite family of conserved quantities. And as I say, Brad has put something in the Slack channel about this. I believe that we may be, well, somebody may be able to help. Yeah. Oh yeah, so sorry. So because this is linear, it's a linear equation, I'm going to look for things that look like, let's say my direction is x, that I'm doing the, so I'm looking for things that look like e to the I mx, a wave number in that direction. Yeah. So all the fluctuations have non-zero m, and the mean has 0m. Sorry. So yeah, we're doing coordinate averaging, and it's the wave number in the direction we're doing the coordinate averaging. Okay, now for if this was purely linear, we'd have, I'll just finish and then, if this was purely linear, then we'd have the pseudo momenta, which I'm sure many of you know about. I'm not going to get into details, but the question is what survives when Q bar, when the mean, where's it gone? When Q bar, okay, I've rubbed off the Q bar equation, is allowed to evolve in the system. Okay, I'm not keeping Q bar fixed like I would do for a purely linear problem. I'm allowing Q bar to evolve, and it's going to evolve in response to the Q prime going to Q bar interactions. Yeah, sorry.
Why do you think the nonlinearity with two inputs?
How many would you like? I mean, it's just to differentiate. I mean, you can. It's really just to say. It's to make an analogy with this kind of thing, really. So you can see straight away that I could have a Q bar, Q prime. That's an interaction of a mean with a fluctuation. If I just wrote it with one input, what input would you like? I don't know. Because they're always quadratic, yeah. So 2 seems to be the natural number to do.
I don't think I realized you were doing quadratic.
Okay, sorry, I said that right at the very start. Yeah, okay, thank you. Yeah, good question then, yeah. Okay, everybody happy? Okay, where's that? So there are a few things you can think of. I spent a lot of time thinking about averaging. Yeah.
Arbitrary phase that you have for fluctuation.
Yeah.
Under these equations are conserved.
Yeah. Invariant, yeah.
So the equation for mean, you will also have to shift the Q bar by.
No, because the only interaction that's going back into the mean is essentially, if you want to think of it, it's the wave interacting with its complex conjugate. So the phase shift cancels. Yeah. Okay, so just a few notes. And at the end of the lecture, I'll show you some situations where we try and describe fully nonlinear dynamics by quasi-linear dynamics and see how well it does. Sometimes it does very well, sometimes it doesn't. But let me just say something about, again, I hope I'm not labeling it, the choice of averaging direction. So imagine, I mean, the kind of problems we're all used to doing. We did a local problem, in a little periodic box. Maybe it's periodic in 2 directions. So for example, in a local, say, Cartesian domain, which might be periodic in 2 directions. I obviously have a choice, right? I could average over both horizontal directions. I might say one of the horizontal directions is more important than the other. And it's not clear I'll get the same results. So this would be, there would be a difference in my quasi-linear equations if I chose one or the other or both. So be a bit careful when people say the quasi-linear approximation works in this case or doesn't work. The choice of averaging direction you may want to think carefully about. So for example, with an imposed shear flow, so if you think about the problem Nigel talked about, which was Couette flow, so you have two walls moving, and then in the other two directions, we have periodic directions. Those two directions are not the same, right? Shear flow. I could do streamwise averaging. Or spanwise averaging. So this is in the direction the fluid is moving. This is perpendicular to that direction. And some people would say it's natural just to do the averaging in the direction of the shear flow, so in streamwise direction, and keep fully not approximating the other direction. Other people disagree, so just be a bit careful. Yeah, I think that's all I want to say. There are examples in the literature of people kind of doing all of these different things. Of course, if I only average in one direction, I've got a three-dimensional system. My mean is two-dimensional, right? I've averaged in one direction, my mean is two-dimensional. If I average in two directions, then my equations for my mean will become a bit more simple. They'll just be in one direction, but I've done more damage to my system. Yeah, sorry. Oh, sorry. I should say I'm not a physicist. I feel a complete fraud coming to this thing. I'm not a physicist, I'm a mathematician. So that means there exists. There is. Mathematicians are inherently lazy. They write, yeah, sorry. Okay, is everybody happy? Okay, you'll be even happier in a minute. I think it's a good time for us to have a break. And let's just have a 3 or 4 minute break. Get yourself a drink if you need to, and we'll come back, and what we're going to do is we're going to generalize this approximation, okay?
A slight question. If you keep only the wave number k, this term g does not generate any k, no?
If I keep only the wave number k,
yeah.
so what I have is, if you have a look here, so yeah, but I've got rid of the k going to 2k.
Yeah,
That's not there.
So my point that you don't need to assume that k is the small amplitude with respect to the
No.
mean flow.
I don't need to assume
That the fundamental is small with respect to the mean flow if you keep only the fundamental.
that's okay. I think you're arguing the wrong way around though, aren't you? Because the question then is, the reason I need to say that the mean is more important than the fluctuation is to say, imagine I've got this zero, so let's say k is 2.
Yeah, yeah.
0 acting with 2
Yeah.
is more important than 2 interacting with -2. I can say that is more important if 0 is much higher amplitude than 2. Yeah. And that's an obvious way of doing it. It's like this is obviously going to be more important than this. If this term's huge, this is huge compared with this, right? And then once I've made the approximation, then everything's self-consistent. And I could, of course, get my k's, the amplitude of my k's quite large.
Yeah.
So there are situations where this is not bigger than this, but it's still self-consistent.
Yeah.
But all I was saying is that if this is true, if this is much bigger than this, then it definitely is self-consistent. Because no matter, this term can always be neglected with respect to this one.
I see.
No worries.
What
wanted to ask about when you, I don't know which slide, but when you were talking about it's hard to know the correlations a priori.
Yeah.
If it's be possible to just do ML on it and then use previous data and then figure out what the correlations
Okay,
are.
we'll come on to that. We'll come on to that.
So it's
Yeah.
gonna help. Okay.
Yeah, because that's what we do.
I'm guessing people have done that already.
Yeah, yeah, absolutely. We look at it and we say, oh, okay, let's work out the correlation length, the correlation time. Oh,
Yeah.
we could have done QL. But it's very hard to know, you know, before you do the calculation that. And so we're trying.
You do it on previous data. You teach the
So
model.
okay, so I'll come on to that.
Machine
If I
learning,
have
so-
time,
Yeah.
I'll come on to that right at the end of the third lecture. So
see.
kind of data driven.
Yes, exactly.
Absolutely.
And then you build models that are trained.
Yeah, is that something you're interested in, data driven?
It's something I've been exposed to.
Okay, okay. So that's something we're definitely thinking about.
Yeah,
So,
yeah. Because
Yeah,
right now, this is what people do all the time.
Yeah, absolutely.
Nice to do things from first principles, but if you don't have access. to
Oh no,
that, then
absolutely,
yeah.
absolutely. So what we're going to do is we're going to kind of derive some equations, and then we're going to, at the end, we might say, well, can we learn the terms, learn the various terms?
Exactly. Yeah. Cool. Okay. Looking forward.
Okay.
So I'm just curious, this infinite U1 symmetry, it only holds in this QL approximation, or it's true for the?
Oh, so it's certainly not true for the fully original system. The fully original system is completely nonlinear, and so you can't do this with the perturbations, because if you include this term here, this one could have one phase, this one would be multiplied by another phase, and then you're going to spread the phase through the whole. Yeah.
Okay. So
it's only quasi-linear.
Right.
Yeah.
And different fluctuations can be shifted by different amounts.
Sorry?
Can different fluctuations be shifted by different amounts?
Yeah.
Oh, okay.
Yeah. So different wave numbers will be, so all the perturbations will be could be shifted by different amounts. And because they only act with the mean, interact with the mean, that's okay. Yeah.
So I have another question. So you say this wall, the QL approximation will now work for the fully developed isotropic turbulence.
No, it won't. It won't because fully developed homogeneous turbulence, it's all this. It's all that. Yeah. And
So-
none of this.
So can I think that if this mean flow Q bar getting smaller and smaller, then we kind of correspond. We have
So
to eventually.
as the mean goes smaller and smaller and smaller, so perhaps if you're looking at turbulence, you go to smaller and smaller scales.
Okay.
Then things turn back into homogeneous isotropic turbulence, and then you have to stop doing this. You have to stop doing whatever it is I'm doing. That's right.
Okay.
Yeah.
Thank you. By the way, I think this is very physics.
Oh, is it? Okay, that's good. Sorry.
All the math is correct.
Yeah,
You're presenting it all in
I find all this very insulting. Well, I haven't gone into Hilbert space yet, so.
Well, and, outside of the field, you really will. Because when you know it, if it comes to solving the equations, you'll have the skills.
Okay, let's see if we can get people back. I'll just have a sip of my coffee. On what I've rubbed off, or?
You might get like.
At the moment, for that, yes. For that, yes. Yeah. And in fact, well, you'll see when we do GQL, the splitting doesn't obey Reynolds rules, but once you take out the interactions that we decided with, it does. Okay, let's see. Okay, everybody ready? Where are you on my notes? Okay. Okay, so that's nice, and we'll show sometimes it works and sometimes it doesn't. But actually, it suffers from quite a large deficiency, and I'll go into that in a minute. So we thought what we would do is try and generalize the quasi-linear approximation. And at the minute, we're generalizing it. The example I'm going to give you, in fact, most of what we've done, we're generalizing it. Think of it in terms of a spectral representation. So we're going to be thinking about coordinate averaging and looking at things in wave number space. So we can write out triad diagrams that look a bit like that. So let me just tell you what the downside of what we've done is. The QL approximation with coordinate averaging so think of this as being zonal averaging. Also doesn't have to be, but it has very limited scope for energy exchange between the mean and fluctuations, and indeed between the fluctuations themselves. So let's try and think about this. So if I had a fluctuation, say at wave number 10, and it interacted with my mean, I'm not going to self-consistently draw these arrows. This just now means interaction with. So if I have 10 interacting with the 0, well, that can put energy back into the 10, clearly, through a quadratic nonlinearity, right? That's all it can do. And within this framework, I could have a 10 interacting with, say, a minus 10 to give me the 0. So my energy is going between, well, here's a fluctuation with a mean, putting energy into the fluctuation, a fluctuation with a fluctuation of the same wave number, putting energy into the mean. There is no way of the fluctuation interacting with anything to put energy into any other fluctuation wave number, okay? And of course, that leads to everything being, you can just split up all the fluctuations and they all have their own dynamics and they only kind of feed back via the mean, via interactions with themselves into the mean. So there is no way scattering energy between the fluctuations. Largely because we got rid of it, right? We just threw it away. Here I could have had a 10 and a 2 putting energy into a 12, right? Okay. So we're going to try and remove this deficiency, but I want to make the equation, the evolution equation for the fluctuation still linear. So I still want to get rid of that term, but I want to put it back in a mechanism for getting energy between the fluctuations. So I'm going to extend to, well, first of all, remove this deficiency. And second, to allow more interactions between, well, I'm going to change the name, but so far I've called them mean. I'll put mean in. Okay, but I want to keep I want to keep the evolution equation for the fluctuations linear. And the reason I want to keep that is to allow for a statistical theory based on these equations, which I'll come back to in the next lecture, okay? Okay, so all I'm going to do is I'm going to generalize what I mean by a mean. And it'd be confusing if I still called it a mean, because it's not going to be a formal mean. I'm just going to call them low modes for reasons that I will explain in a minute. So what I'm going to do is, instead of setting Q is Q bar plus Q prime, I'm going to set Q. I'm going to do a different decomposition. These are going to be called low modes, and they're so called because they have low wave numbers. And these are going to be called high modes. Okay, so I'm just going to put an arbitrary threshold on my wave numbers. And if my wave number is smaller than that threshold, I'm going to call it a low mode. If it's bigger than that threshold, I'm going to call it a high mode. And I'm going to have different rules for the interactions depending on whether I'm a low or a high mode. So let's imagine I'm doing this in the X direction. I might set QL to be all those wave numbers. So it's going to be the sum over all those wave numbers between minus lambda and plus lambda. So I'm still carrying around my other two directions. Yeah. Okay, so my low modes are just going to be all those modes with wave number smaller than or equal to lambda. Okay, so if I set lambda equals 0, my low modes are the same as my mean modes that I had before. Okay, and my high modes, well, they're going to be all the others. So I'm just going to write this as Q minus Q low. Okay, is everybody happy with what I've done? Because it's fairly key. So this is it. Yeah.
It's the first step.
So this is what Baylor called spectral filtering, right? I've just kind of filtered, and I've called one set of things low modes and one set, and then the other things high modes. So we said at the end of last time, if you do spectral filtering and you work out the nonlinearities, and I said you could go away and try it, that it didn't satisfy the Reynolds rules, right? So just remember this. So note, as written, or if I don't do anything else, the partition, unless lambda, this lambda really is 0, does not satisfy Reynolds rules. Because if I take products, then they can appear in the wrong place. So you can go away and try it. However, what we can do is we can remove some of the triad interactions kind of in the spirit of what we were doing. And that's what I'm going to do now. So let's go back over here. So we can remove triad interactions a la Creighton, in the spirit of QL. We're going to move them in pairs. And so let's just write out the triad interactions that we can have. In the notes, it's going to be done in a fancy way. I'm just going to try and give you an idea. So what are the triad interactions we could have? We could have a low interacting with a low to give me another low. So for ease of thought, let's imagine I put my threshold lambda at 3. Okay, so 0, 1, and 2 are low modes. So I'll put it at 2. 0, 1, and 2 are low modes. Everything else is a high mode. So this could be a 1 with a 1 interacting with a 1. Sorry, interacting with a 1 to give me a 2. That's low, low going to low. That's going to be allowed. Okay, I could have a low with a high to give me a high. Okay, so this could be, well, this is very similar to one I kept before, which was the mean with the fluctuation interact to give me a fluctuation. So this could be a 1 with a 5 to give me a 6. This is going to be key. You see, I've automatically scattered something from a 5 to a 6. So this is going to be key. A 1 with a 5 to give me a 6, I'm going to allow that one. Or I could have a high with a high to give me a low. Okay, so that could be a 10 with a minus 11 to give me a 1. Or yeah, minus 10 with an 11 to give me a 1. That's going to be allowed too. And that's an analog of the other one we kept. So I'm going to keep all of those. Okay. And I'm going to get rid of the low with the low to give me a high. We didn't have that one in there before. That wasn't an that wasn't an interaction. But here I could have a 1 with a 2 to give me a 3. I'm not going to allow this one. Okay. I'm also not going to allow a, well, this is the one I didn't allow before, a high with a high to give me a high. So that's a 10 with a 10 to give me a 20, for example. And that was the one which was thrown out before. So I'm not going to allow this one. And I'm also not going to allow a so if I can write this the right way around. What have I got left? Low, high, giving low. Thank you. I'm not going to allow that. Thank you. Good to see somebody who's paying attention. It's nice. Even if it's not me. And the reason I should have been able to work that out is because if I take out this one, I definitely need to take out this one because this is like triad decimation in pairs. This one's got 2 lows interacting with a high, as this one has. If I drew it in terms of arrows going the right way, I know that if I take out this one, I have to take out this one. Okay. So 2 things. Taking out this one ensures that the equations in the high modes are linear. Taking out these 2 allows you to obey Reynolds averaging rules. Okay. If you stick to these interactions. Okay. So, okay. The equations for these look something like this. equations look like, I can write down an evolution equation for the low modes. So I have my linear operator acting on my low modes. Then I'll write it out and I'll explain what this notation means. So just let me explain what this term is. This is the nonlinear interaction of a low with a low going to a low. Okay, that's what that notation means, yeah?
We have one question on the diagrams on the left. So the second one in the first row and the last one in the second row. They look actually quite similar. We got low and a high, and they add up in either low or high.
Yeah.
So it seems quite arbitrary that we delete one of them.
Well, it may seem quite arbitrary, but this is one we have to keep. This is one we have to get rid of if we get rid of this one. So, okay, you can argue about whether it's a good thing to do or not, but if you're doing triad decimation in pairs and you want to conserve things like quadratic invariance, you have to do something to make sure that your energy isn't just lost in the system. So you have to kind of take out these things in pairs. Okay, so just again, the notation, this is a low interacting with a low to give you a low. That's what this notation means. And of course, I've got the high interacting with the high to give me a low. This is the key term. Remember, the key term is what are the effects of the fluctuations doing on the mean? So this is the one we really want to know what it is. And then we have an equation, an evolution equation for the high modes. Of course, we have the linear term. And we have two terms which look like the interaction of low with high to give me high. These are kind of symmetric terms, just not high. Okay, I have no idea what the last number I wrote down was, but 16 is where we're up to. Okay, so you can see, what can you see? You can see we've taken out triads in pairs. We have an equation for the evolution of the high modes that is linear in the high modes, or quasi-linear in the high modes. Okay, so we're kind of happy. Okay, so a couple of things to note before I show you some pretty pictures of how these things do. The reason we're going to do this, we'll see in the next time, is that we're going to try and write down equations for, essentially, we're going to derive evolution equations, statistical equations for the evolution of these kinds of things. Okay, that's what we're going to try and do. So we're going to try and get a hierarchy of statistical equations. It's going to be easier to do that if the equation is linear in the high modes. So note, we still have triad decimation in pairs. So everything that we wanted to be conserved is conserved. If I set lambda equals 0, I go back to QL. If I set lambda to be, I don't know, the spectral representation, the full spectral representation of the whole system, I go back to the fully nonlinear system. So if I was doing this numerically, I'd be going back to doing DNS. So this parameter lambda it's a parameter which gets me from quasi-linear theory, if you like, all the way to doing DNS. So that's a kind of interesting parameter to play along with. And this is the key point, that if I have a high mode of 10 interacting with a low mode of 1, that can scatter energy into, 11. Right? And so there is a mechanism for scattering energy from the fluctuations into the fluctuations via interaction mean or with the low mode. And of course, I could have a high of 10 interacting with a high of -11 to put the energy into 1 or -1, whichever way you want to look at it. Yeah. So of course, this is a high mode. This is a low mode. And this is going to be key. We'll see that if GQL does better than QL, it's because it's allowing this kind of energy interactions. Okay, so just to finish off the notes, over the past few years, we've been trying to work out when QL and GQL work, or if they work at all. So there are many numerical tests. Put some references down. So the first paper which looks at this and derived GQL is a paper by Greg Cheney, Brad, and myself. And we were looking at the stochastic driving of jets. This paper. And there's been a lot of work recently on 3D plane Poisson flow, which again is one of the paradigm problems Nigel was talking about by student of Greg Cheney's, Colleen Kalam. It's in her thesis. And there's been work at Imperial College as well. And they look at the effects of choosing different averaging directions, whether you're averaging one direction or another. So I'm going to show you some pictures now, I think. Oh, okay. One more. These are the ones I'm going to show you. So we did some work on what's called the Busse annulus. So I have to explain to you what the Busse annulus is. This is work with Jeff Oishi using Daedalus and Brad. So you all saw Jeff in the first week. Okay, and just to summarize the results, which I'm just going to quickly show you. GQL always improves on QL, but it's not monotonic in lambda. So you might think lambda bigger and bigger, you get better and better results. And it doesn't happen for reasons I will try and explain. Okay, so at this point, I need the board. So I'll just spend the final 10 minutes showing you pretty pictures. You tell me what it is. I just decide before the. So you always do that if you're doing a numerical calculation. It's like the highest spectral mode you're keeping in your calculation.
Well, once you set a cutoff, you allow all the nodes to interact.
Sorry, can you say the question? Yeah, essentially you allow the modes to interact such that they're solving the equations that have just disappeared in here under there. Yeah.
This might be a tough topic, but I'm wondering why the interaction of 10 and 1 doesn't also give 9.
Oh, well, okay, it would. 10 and -1 in my notation would give 9.
So,
yeah.
So choosing 11 is just a.
That was just an example. That's an example of So it also scatters energy into 9. So eventually you're going to get energy scattered into all the high wave numbers. If I start off with, yeah, so that's a really great question, because before, if I started off with just energy in 5, it stays in 5, goes to 0, comes back to 5, that's it. If I start off with energy in 5 and 0 and 1, 5 gets me to 6, 6 gets me to 7, 7 gets me to 8, etc., etc. Okay. Okay, we don't need.
It's funny because it's like similar to de-aliasing, like by throwing away some of the modes so that you're not bringing like random noise in.
Right.
But it's in detail slightly different because there's one mode that's different. You allow some things that you wouldn't allow in de-aliasing, which is kind of an odd business.
But also you're very careful about which interactions you keep.
Exactly.
I mean, and that's the key. I mean, that is really the key. I remember Brad and I sitting in the Isaac Newton Institute, there's a foyer there, you know, trying different combinations, thinking they didn't work. And eventually it was like, one of them worked, and we were kind of like, okay, we can go for lunch now. That was it. You know? Okay, so now I'm going to show you an example because I just thought it was cool on this problem here, the Bussard annulus. So I have to explain to you what that is. And so let me just go back to here and then do. Okay, this is a model for the driving of the zonal jets in Jupiter. You remember I told you there were two types of models, one of which they were deeply driven, one of which they were shallowly driven. I'm not going to go into real detail. I don't know, Keith, did you talk about this model? No. Okay. I'm not going to go into details about where this model comes from. It's a model that went back to Bussard over 40 years ago. And this is a model for driving of deep jets in convection. And remember everything you've been taught in all of Keith's lectures. If you have a ball of fluid and you rotate fast enough, then you get essentially geostrophic balance, okay? Geostrophic balance means two things. One is that, or rapid rotation means two things. One of which is that the velocity, the fluid wants to line up in what are called Taylor columns, parallel to the axis of rotation, okay? And the second is that in geostrophic balance, the Coriolis force is largely balanced by the pressure, okay? So these are the equations of rotating convection. I haven't made any approximations yet, except for the Boussinesq approximation, which is actually not a great approximation to make for Jupiter. You really need an anelastic approximation to go from, you know, there is a lot of density stratification that happens there, but let's not worry about that in a minute. I have different driving parameters. This is the Rayleigh number that Nigel talked about for driving and convection. The Ekman number, I'm sure you mentioned the Ekman number, Keith, yeah, I did, is the ratio of diffusion to Coriolis force, and then there's a thermal Prandtl number in the problem. And what you do is you make use of the fact that you know that the solution looks like this, and it's kind of two-dimensional. It's kind of two-dimensional, not in the sense of Baylor's kind of thin layer. This is kind of two-dimensional because rotation makes it two-dimensional. Rotation makes it want to be, not depend on the z-axis, but depend on, if you think about these things as being x and y, or in cylindrical polars, s and phi, or whatever, yeah? So it depends on s and phi, and not a lot on z. Okay. Unfortunately, it doesn't quite work because, of course, you have to satisfy a boundary condition here. And satisfying the boundary condition here brings in terms in a way that I'm not really going to have time to explain. The fact that there is a boundary condition there, and it slopes, and the height of the column, if you like, the height of how far you're going changes as you change x and y. That brings an extra term into the equation, and the extra term it brings into the equation is a term which, well, I'll show you. What do? Okay, you say your velocity is largely geostrophic plus a perturbation. You say your temperature is just going to depend on X and Y, and you say your non-geostrophic bit is much smaller than your geostrophic bit. You say I have to satisfy a boundary condition at the top. I'm going to approximate that boundary condition of a kind of curved boundary with a sloping boundary. And for those people who want to know the details, you can look in the papers with a straight boundary, although you can make, actually, there's no problem with making this curved. And then you turn the handle, you derive lots of, you do lots of algebra, and you derive a set of equations that look like this. So I'll just explain what we're evolving here. This is the vorticity in the plane, if you like. And these terms look familiar. This is the nonlinear term. This essentially is the term that you get. This is the term that you get because we have a sloping boundary. That is only there because the boundary is sloping and we're rotating. And this is very similar to the, well, it's the same as the term you get when you do the shallow problem on a thin layer, the kind of beta plane turbulence, the barotropic beta plane. And that's why it's very hard to theoretically disentangle which of these theories is right, because the equations look kind of similar. I have thermal driving, and then I have different frictional terms, which I'm not really going to talk about. And I'm coupling that to an evolution equation for the temperature. So the temperature is advected around. This is the interaction with the mean temperature, and this is diffusion. And this is the Jacobian. So these two terms are the nonlinear terms. Okay, so what are the kind of dynamics, the fully nonlinear dynamics you can get with this?
Sorry, is the core also a boundary condition?
No.
It's just rotating from the outside in.
Rotating from
Sorry,
the outside.
where so is there a different, like, which part are you solving?
So imagine I'm doing this, okay?
Yeah.
Then I could solve it in a cylinder, in a disk if I wanted to. No, I don't need the curvy top. I'm just going to solve it in this plane. Sorry. Yeah. And so I have an inner boundary and an outer boundary, and the inner boundary is going to be, you know.
But you're not solving like up at the pole.
No. I'm just, well, because it doesn't matter. I'm solving it everywhere because it's the same everywhere. You see what I'm saying? It's not really the same everywhere, but I get these terms that come in because it's not really the same everywhere. Okay. So what do you get? Well, I have convection. It's interacting with rotation. So I get the convection driving Reynolds stresses. So these terms which are going to lead to, so the convection is going to have correlations in there, and that's going to drive large scale flows, hopefully. These are going to take the form of zonal shear flows, and then those zonal shear flows will act back to modify the convection. Okay. So as I put down here, as the convective driving is increased, convection sets in for more than some critical Rayleigh number. The convective cells interact with rotation via that term, that beta effect term that I came in because I had sloping boundaries. Okay, you can think of these as nonlinear Rossby waves, this kind of convective cells or turbulent eddies. They're going to drive a Reynolds stress. The Reynolds stress is going to drive a shear. So this is a bit like what we saw with Nigel's predator-prey thing. The shear comes back and inhibits the convection. And depending on what parameters, you can get a wide variety of behavior. And there's a lot of work on this. So here I've just put up 3 different sorts of behavior you can get. I'm not going to go into detail because we only have 5 minutes left. So we can get what we've called quasi-steady large jets. So what I'm doing here is plotting what's called a Hofmöller plot. So I've got the behavior of the large scales as a function of y and time. So this is a large scale zonal flow or shear flow. This is, if you want to think of it, this is the inner boundary. This is the outer boundary. I'm plotting the zonal flow velocity. I can get multiple jets. I can get something which looks a bit more like Jupiter. I can get things where It's reversing. What does this reverse? It reverses. I have 1, 2, 3, 4, 5, 6, 7 jets just by changing the parameters. Or I can get this behavior here. This is interesting. It's not quite clear, but you can see it from the back. But what happens is I get this behavior where a jet comes along, it kills off the convection. The convection is no longer a source for the jet dies away. So the convection comes back, the convection drives a jet. And this is like, you can see this red switching off, red switching off, red switching off. This is bursting behavior. This is very similar to the predator-prey dynamics between zonal flows and convection, a similar kind of predator-prey dynamics to the one that Nigel talked about. So how well, okay, I've spent 90% of the lecture talking about interactions. How well does QL do, or GQL do, at reproducing this behavior? So let's start off with the simple case of just quasi-steady large-scale jets. So what happens, I'm just reminding you of what the fully nonlinear solution is. What happens, at least for this case, is that QL gets the wrong number of jets. It's not getting the interactions quite right to get the correct number of jets. However, as soon as I put my threshold at 1, I get the right number of jets, okay? And I get something that's very close to the right solution. And the reason is I'm allowing, I can't show you what exactly, the exact interactions. I'm allowing interactions to put energy into all the right modes or all the high modes. So they keep going in the nonlinear interactions. I didn't need to increase lambda to 5, but I thought I would do. And so things don't get much better as I put lambda equals 5. You may be wondering why this one was blue and this one was red. This one's blue and this one's red and this one's switched. There's a symmetry between top and bottom. I could have got jets of either sign. Just so happened that this one was the wrong sign, but I'm an honest kind of chap, so I thought I'd still put this in the paper. I got one of the opposite symmetry. What about the multiple jets? Well, this was what happened when I did the DNS. Remember, I had 7 jets, or whatever, 1, 2, 7 jets. QL still gets nice number of jets. It's still doing quite well for a quasi-linear theory. I don't think that's too bad. Gets strong jets. It gets the wrong number though. 2, 3, 4, 7, 8, 9. So it got the wrong number. By the time I put lambda equals 1, I do get the right number of jets. And 5 doesn't really, it gives you more of the variability, but doesn't really improve too much on 1. And then the final one, which I thought was kind of interesting, is the bursting behavior. Now, I was very surprised, or I would be very surprised if any kind of quasi-linear theory would be able to get bursting behavior. It turns out that quasi-linear theory, at least here, has no chance whatsoever of getting this kind of behavior. And we have other examples of bursting where quasi-linear dynamics just can't describe it. Even putting lambda equals 1 didn't really help. In fact, it made things worse. But by the time I put lambda equals 5, GQL, I could really reproduce this bursting type behavior, which is a very highly nonlinear thing to try and reproduce. So at least from these numerical simulations, somebody was asking me in the break, how can you test these things? All you can do is nonlinear simulations and try and compare them with the real world. GQL does seem to improve on QL, okay? And the reason, I think the reason to keep, even though it's linear in high modes, the reason is really it's allowing these kind of eddy scattering processes to occur. Okay, I think I'll finish there and wait for questions. Yeah.
How to know what's the cutoff rate number?
Yeah, we don't. Except 1 always does a lot better than 0. And that we understand is because as soon as you have one, you can scatter energy into all the other ones. Because as soon as you have one, you can get two. As soon as you have two, you can get three, etc., etc. So you can get energy into all the other modes. Sometimes, and I don't really want to get into details, sometimes adding more modes doesn't help. And you can get into a case where you've got so many modes in the low modes, they take up all the energy, they don't put any energy into the high modes, and your system just looks like an under-resolved DNS. You don't want that.
When you were doing these, for your high mode cutoff, did you end up just using the same as the DNS?
Yeah,
mode?
yeah.
Who else used that?
So I want to stress that these calculations, they don't save you anything. Well, they save you a little bit. They save you a little bit, but they don't. Oh, blimey, it's Adrian. They save you a little bit, but what they will do is allow you to do the closure because you kept the, and that's where the savings will potentially come if you wait for the next lecture, possibly. Yeah. So
you say that when we include all the modes, basically QL becomes BSS.
yeah.
So what is this whole?
Oh, so this is, yeah, all the modes are included. So lambda is infinity, if you like, or NX. And that's equivalent to DNS. Sorry, that's what I was trying to say there.
So basically the number must have it in mind.
Yeah, it's for this like 128 or something. Or,
Oh.
yeah. Baylor and then at the back.
So how do you do for like predictability timescale or something that tells you about the chaotic aspect of the bursting?
How? Yeah. Oh, right.
So how well is the?
Yeah, actually, once you get the bursting right, you pretty much get it right in terms of the timescale. Yeah. At the back, and then Ellen, I'll come to that side of the room in a minute. Yeah.
So thinking about the triad diagram disallowed, the ones that you disallowed, seem like they could be thought of as separation of scales that you can never have two lows going to a high.
Yeah. That's very, very. Yeah.
I guess my question is that a reasonable physical picture related to what you have written below? Is that also a kind of separation of scales that allows you to impose that, or are those things?
Oh, okay. The answer to your first question is right. You're kind of enforcing a See, in spectral space, the only true separation of scales you have is between k equals 0 and the rest. I mean, formally, if you're a mathematician, that's all you could ever take. And what we're doing by taking out these other interactions is somehow enforcing some kind of separation of scales, not formally, but that's very true. And your second question, I don't think so, but I'll have to think about it. It's a really good question. Yeah. Yeah, Helen.
Is there any sensitivity to what you actually project on in the way of modes? So I guess you've been talking about Fourier modes, but
yeah, that is the good question. So we've been thinking a bit in Greg, and I think some of Greg's students here are thinking about other ways of implementing GQL using other modes, or perhaps, if you were doing this in engineering, you'd want to do it in a funny shaped domain, not doing spectral decompositions. Can you do it with Gaussian, something else? We're thinking about all of that. And the answer to your question is, I don't know what the sensitivity would be. This is the cleanest thing you can do when you have a periodic signal. But maybe, I don't know, I'm thinking some of Baylor's things about you've got oceans and using structure. I mean, there's all sorts of things you can think of. Wavelets, yeah, we're thinking about wavelets. It's good. Yeah.
So I wanted to contrast this with our earlier lectures on subgrid modeling, where
Right.
you're just restricting the wave numbers down to some k. So here we keep some simplified model of the high modes.
Yeah.
So how does this do better? Or what is the difference? They're seemingly almost the same, but not quite.
Okay, if you wait 23 hours or nearly 23 hours, we'll come back to exactly that, because what you would really want to do is, I don't want to do this. I don't want to solve for all the high modes if I can help it. What I need to do is somehow parameterize their effect back onto the low modes. And you could think of that as subgrid modeling, or you could think of it as writing down equations for the statistics of the flow. And that's what we're going to be doing. So if you just hang the fire, we'll come back to that. Keith.
The example showed you select the next one. There is this separation of the underlying fluctuation for also showing the anisotropic scale.
At least the largest ones. Yeah. Yeah. Yeah.
There are other examples where
So the example I have, which is closest to not being of this type, because I'm kind of interested in anisotropic flows, so I tend to put them. So we did rotating Couette flow, which has I mean, it's rotating, so, but it's not like this massive. And that one is similar kind of thing. And this one, these guys looking at plain Poisson flow. Okay, there's still anisotropy because of the shear flow, but there's not this characteristic of rotation, which is trying to send energy one way rather than the other. And so, yeah, you can do it for both cases of a forward type of cascade, or yeah, and you seem to get, in a sense, I think the ones where it's going forward are easier because you've got your mean flow there to start off with, and so you've got something, you know, if you've got a beefy shear flow, as it were, then you know your first cumulant is there. Oh, sorry, your mean interacting with your fluctuation is there from the start, right? It's really there from the start, and things can start off doing well. Here, I actually have to build up a mean. So at the start, there's no way anything's right. But once I build up the mean, it should get better and better and better. Okay. Oh, one last question.
So, is it possible to see the energy cascade in the for example, in the high peak?
Yeah, so you can look at the spectra. You could look at transfer functions. So actually, let me just. Okay. I can't remember what I put in here. I can't find my cursor. Okay, I have a postdoc who did this problem, which is a different kind of problem, and we were interested in that. Okay, he's still working this out, but he did exactly that. He worked out transfer functions. I'm not really going to go into any details, but it's exactly right. How did the transfer functions change as, you know, you go from nonlinear to QL to GQL? Because of course you're cutting out channels for energy to. So yeah, you're right. You can look at it, and we have, not for that problem though, for a different problem. So. Oh, well, you're in the spectra, that kind of thing. Yeah. So once you get it right, you get the spectra right, pretty much. Yeah.
Because one of the interaction broke down kind of the scale of locality.
Scale of, sorry.
Scale locality. So you have.
Oh, scale. Yeah. So you're allowing you're disallowing local in wave number interactions, but you're allowing non-local in wave number interactions. And what's interesting is that seems to be enough when you have a strong mean. It's not going to be enough when you don't have a strong mean. I say again, this will not work for homogeneous isotropic turbulence to get spectra correct. Okay, I think it's time for another coffee. So thanks all for listening. Oh.